They say history is a straight line. That progress moves in one direction, from ignorance to enlightenment, from primitive tools to modern science. But the archaeological record tells a different story. Carved in stone, written on papyrus, and forged in ancient fires are discoveries so advanced, they challenge our entire understanding of the past. These are the scientific facts that ancient civilizations knew, long before the so-called modern era began. It's math, before math as we know it even existed. On clay tablets baked under the Mesopotamian sun, we find evidence of Babylonian trigonometry, a full 1,000 years before the Greek astronomer Hipparchus, often credited as its father. A tablet known as Plimpton 322, dated to around 1800 BCE, isn't just a random list of numbers. It is a trigonometric table, displaying a sophisticated understanding of ratios and right-angled triangles. The Babylonians used a base 60 system, which allowed for remarkably precise fractions. This wasn't just theoretical math. It was practical knowledge, likely used for calculating land surveys, architectural plans, and predicting astronomical events. They had mastered the relationships within a triangle, a foundational concept of modern engineering and physics. Nearly 4 millennia ago, they knew the scale of our planet without ever leaving it. In the 3rd century BCE, in the Great Library of Alexandria, a Greek scholar named Eratosthenes conducted an experiment of staggering genius. He had heard that on the summer solstice, the sun shone directly down a well in the city of Syene, casting no shadow. At that exact same time in Alexandria, hundreds of miles to the north, he measured the shadow cast by a vertical stick. The angle was about 7.2 degrees. Knowing that 7.2 degrees is 1/50th of a full circle, he reasoned that the distance between the two cities must be 1/50th of the Earth's total circumference. His final calculation, made using little more than sticks, shadows, and intellect, was astonishingly accurate, estimating the planet's circumference with an error of less than 1%. They conceived of atoms long before the invention of microscopes. In ancient India, around the 6th century BCE, the Vaiseshika school of philosophy developed a theory of atomism that was startlingly prescient. The philosopher Kanada proposed that all matter was composed of anu, or indivisible particles. These particles were eternal, indestructible, and could combine in various ways to form different substances and even complex objects. This wasn't a physical theory derived from experimentation, but a philosophical one born from a logical inquiry into the nature of reality. Yet, the core concept, that the world is made of fundamental, unseen building blocks, would not be proven by Western science for another 2.5 millennia. They predicted the heavens without the aid of telescopes. The Maya, a civilization that flourished in Mesoamerica, were master astronomers. Their understanding of celestial cycles was so profound that they could predict solar and lunar eclipses with incredible accuracy. They didn't have lenses or advanced optics. Instead, they had mathematics and time. Using complex, interlocking calendars like the long count, they meticulously tracked the movements of the Sun, Moon, and Venus over vast periods. The Dresden Codex, one of the few surviving Mayan books, contains detailed tables predicting exactly when eclipses would occur. This knowledge wasn't just for ceremony. It was a demonstration of cosmic order and a tool for wielding power. They practiced a form of medicine before modern medicine was a concept. Long before Edward Jenner's famous work with cowpox in 1796, physicians in China were already fighting smallpox with a revolutionary technique. As early as the 10th century AD, they practiced variolation. This involved taking dried scab material from a person with a mild case of smallpox and introducing it to a healthy person, often by blowing the powder into their nostril. The goal was to induce a less severe infection that would grant the patient lifelong immunity. It was a risky procedure, but it was the world's first documented method of inoculation, a foundational idea in immunology, developed centuries before its Western discovery. It was an engine before the age of engines. In the 1st century AD, in Roman-controlled Egypt, an inventor named Hero of Alexandria designed a device that seems to belong to a much later time. It was called the eolipile. This device consisted of a sphere mounted on a pivot, with 2 bent nozzles pointing in opposite directions. When water inside the sphere was heated, steam would shoot out of the nozzles, causing the sphere to spin rapidly. Hero's eolipile was the world's first known steam-powered engine. While it was treated more as a novelty than a practical power source, it demonstrated a clear understanding of the principle that would later drive the Industrial Revolution, converting thermal energy into mechanical motion. They built structures that move in order to survive. The Inca Empire, nestled in the seismically active Andes Mountains, developed a form of earthquake-proof engineering that remains a marvel. Instead of using mortar, their master masons cut massive stones with such precision that they fit together perfectly, like pieces of a puzzle. The key was in the joints. The stones were cut in polygonal shapes, with slight convex and concave surfaces that locked into one another. During an earthquake, these stones could dance, moving and settling in response to the seismic waves without collapsing. The moment the tremor stopped, they would slide back into their original positions. It was a dynamic, resilient architecture, 1,000 years ahead of its time. They used scalpels before the first hospitals were built. Archaeological digs across the Roman Empire have unearthed caches of advanced surgical tools that are hauntingly familiar. Made of bronze, iron, and even silver, these instruments included scalpels with interchangeable steel blades, bone levers, forceps for extracting tissue, and specialized hooks. Many of their designs, from the shape of the grip to the angle of the blade, are so efficient that they mirror the instruments used by surgeons today. This wasn't primitive butchery. It was a sophisticated medical practice. Roman physicians performed procedures ranging from cataract removal to complex amputations, armed with a toolkit that wouldn't look out of place in a 21st century operating room. They held lenses in their hands long before the invention of glasses. A crystal object, polished and ground with remarkable skill, was unearthed in the 1850s from the Assyrian palace of Nimrud. It dates back nearly 3,000 years. Known as the Nimrud lens, this piece of rock crystal is shaped into a convex lens, capable of magnifying objects by a factor of 3. While its exact purpose is debated, its existence is undeniable. Was it a magnifying glass used by a craftsman for intricate work, a fire starter, or part of an early telescope? We may never know for sure, but we do know this. Ancient Assyrians had mastered the principles of optics and manufactured a lens, demonstrating a grasp of physics thousands of years before Leeuwenhoek or Galileo. They detected earthquakes without using a single electronic sensor. In the year 132 AD, the Chinese court was presented with a magnificent bronze vessel. It was decorated with 8 dragons, each holding a bronze ball in its mouth. Below them sat 8 toads with their mouths open. This was the Hufeng Dedong Yi, the world's first seismograph, invented by Jiang Heng. The genius was inside. A complex pendulum mechanism at the center of the device would remain perfectly still during normal conditions. But when a seismic tremor arrived, even from hundreds of miles away, the pendulum would swing in the direction of the quake, triggering a mechanism that caused one specific dragon to drop its ball into the mouth of the toad below. It didn't just detect a quake. It indicated its direction. They wrote the first medical oath, establishing a moral code for healers. In the 5th century BCE, a Greek physician named Hippocrates revolutionized medicine by asserting that diseases were caused by natural processes, not by the whims of the gods. But his most enduring legacy may be ethical. The Hippocratic Oath, a text attributed to him and his students, established a sacred duty for physicians. It bound them to act only for the good of their patients, to preserve their privacy, and to do no harm. This radical idea that a healer has a profound moral responsibility created the very foundation of modern medical ethics, a code that still guides the hands and minds of doctors worldwide. They carved advanced mathematics directly into stone. We often credit the Greek mathematician Euclid with formalizing the principles of geometry around 300 BCE, but new analysis of ancient Babylonian tablets shows they were solving complex geometric problems over 1,000 years earlier. One tablet, known as Say 427, is dated to between 1900 and 1600 BCE. It is a cadastral document, a land survey that uses what we now call Pythagorean triples to define precise right-angled boundaries. This isn't just an approximation. It's a demonstration of applied geometry, a proof of concept carved in clay that predates the formal Greek proofs by a millennium. It was brain surgery, performed without anesthesia as we know it. Across the globe, from ancient Peru to Neolithic Europe, archaeologists have found skulls bearing the unmistakable marks of trepanation, practice of drilling or scraping a hole into the cranium. For a long time, this was dismissed as a crude ritual. But the evidence of bone regrowth around the edges of these holes tells a shocking story. Many of the patients survived. Some even underwent the procedure multiple times. While the reasons remain a subject of debate, whether to relieve pressure, treat head injuries, or release spirits, the fact remains. Ancient surgeons possessed the skill to operate on the human brain and have their patients live to tell the tale. They created ice in the middle of the desert. In the scorching heat of the Persian landscape, ancient engineers achieved the seemingly impossible: refrigeration. By 400 BCE, they had perfected a structure called the yakchal. Part of it was a massive cone-shaped dome made of a special mortar that was both waterproof and highly insulating. Below, it was a vast underground storage space. During the cold desert nights, water was channeled into shallow pools near the structure, where it would freeze quickly. The ice was then harvested and packed into the yakchal, often with insulating materials like straw. This passive cooling system was so efficient it could keep ice frozen year-round, providing a source of refrigeration for food and refreshment in one of the world's harshest climates. They invented the most powerful number in existence. For centuries, mathematics in the West struggled without a crucial concept: the number 0. But in India, as early as the 7th century AD, the idea of shunya, or emptiness, was formalized into a number in its own right. The mathematician Brahmagupta established the basic rules for using 0 in calculations, defining it as the result of subtracting a number from itself. It was more than a placeholder. It was a value. This conceptual leap, which would eventually travel to Europe through the Arab world, was the final piece needed to create the decimal system we use today, unlocking a new universe of mathematical possibility. It is perhaps the first analog computer. Discovered in a Roman-era shipwreck off the coast of a Greek island, the Antikythera mechanism has been called the most complex piece of ancient technology ever found. Dating to the 2nd century BCE, this shoebox-sized device is a bewildering maze of at least 30 interlocking bronze gears. For decades, its purpose was a mystery. But modern imaging has revealed its function. It was a sophisticated mechanical calculator designed to predict the positions of the sun, the moon, and the planets. It could track lunar phases, predict eclipses, and even model the irregular orbit of the moon. Nothing approaching its complexity would be built again for over 1,000 years. They understood navigation before the age of maps. Long before detailed sea charts, Chinese mariners had a secret weapon. As early as the Han Dynasty in the 2nd century BCE, they knew about the strange properties of lodestone, a naturally magnetized piece of the mineral magnetite. They discovered that if a piece of this stone was suspended, it would always align itself along a north-south axis. Early compasses were often shaped like a spoon, balanced on a bronze plate. This understanding of magnetism provided an invaluable tool for navigation, orientation, and feng shui, allowing for travel and construction with a directional certainty that was previously impossible. They engineered public health systems before they knew about bacteria. The Roman Empire was an empire of cities, and cities produce waste. To sustain massive urban populations, the Romans built one of the greatest sanitary systems in history. An extensive network of aqueducts, stretching for dozens of miles, brought a constant supply of fresh water into cities for drinking and for public baths. Simultaneously, the Cloaca Maxima, the greatest sewer, and other covered drainage systems carried waste and runoff out of the city and into the Tiber River. They didn't know about germ theory, but they knew that sanitation reduced disease and foul odors, enabling a level of urban density unparalleled in the ancient world. The ancient Maya calculated the length of the solar year as 365.2420 days, a value astonishingly close to the modern scientific figure of 365.2422 days, a difference of just 2/10,000ths of a day. This accuracy was achieved over 1,000 years ago using naked eye observations, without telescopes, mechanical clocks, or modern mathematics. Their calendar system combined multiple cycles, including the Hobbs solar calendar, the Dzogchen ritual cycle, and the long count, allowing them to track days across centuries with extraordinary consistency. This precision wasn't academic. It governed agriculture, religious ceremonies, royal events, and astronomical predictions, aligning human activity with seasonal change. A miscalculation of even a few minutes per year would have accumulated into major seasonal errors over generations, but Maya records show no such drift. Their system stayed synchronized with the solar cycle for centuries. Without modern instruments, how did the Maya measure time so accurately, and what observations are we still underestimating today? More than 2,000 years ago, metallurgists in southern India were producing wootz steel, a material of such quality that it later became famous in the Middle East as Damascus steel. Modern microscopic analysis has revealed that wootz contains nanoscale structures, including carbon nanotube-like formations and cementite nanowires created through carefully controlled heating and cooling cycles. These internal structures gave the steel exceptional hardness, flexibility, and edge retention properties that modern metallurgy would not fully explain until the 20th century. This was not accidental craftsmanship. wootz production followed precise recipes: specific ores, plant-based carbon sources, sealed crucibles, and tightly regulated temperatures. The result was steel strong enough to hold a sharp edge, yet flexible enough to resist shattering, making it highly prized across Asia, the Islamic world, and Europe. If ancient metallurgists could create nanoscale structures without scientific theory, how much practical knowledge existed long before modern science could describe it? History didn't forget these discoveries. We did. If ancient people achieved this without modern tools, imagine what else is still waiting to be rediscovered. Thank you so much for watching this video. Don't forget to hit the like button, subscribe to our channel, and share this video with fellows. Your support helps us bring you more captivating content like this.